Hello everyone and welcome to GIS. Today in this video you will learn what is projection and the types of projection that are being used in GIS. At first, let us understand why we need projection. Now the problem is that the Earth is 3D. It's a sphere and we often want to present the maps on the flat piece of paper or on a computer screen. Therefore, we need coordinate reference system or a spatial reference system which defines the translations from 3D to 2D coordinates. So you want to go from the 3D coordinate of the globe to a 2D coordinate system on a computer screen or on the paper. As you can see in this figure, the 3D globe has been converted to 2D in a plain sheet of paper. So let's understand this in a very fundamental term. For example, I have a globe and consider that globe to be transparent. Now, if I have a light at the center of the globe and draw the lines of latitude and longitude around the globe, what would happen? If I have a sheet of paper and project the light from the center of it, all the latitudes and the longitudes that I have drawn on the globe would be projected on the paper. So that is what is basically projection. When we try to represent three-dimensional surface or earth surface on a flat sheet of paper. To represent the coordinate system on the globe, we use latitude and longitude coordinates and degrees, where 0-degree latitude is defined as the equator. When we move towards the North Pole, the values increases positively towards 90-degree north on the North Pole and negatively towards the South Pole with minus 90-degree on the South Pole. For the longitude, 0-degree is defined as the prime meridian of the Greenwich. The values increases positively towards the east with 180-degree around the international date line and negatively towards the west. We call this a geographic coordinate reference system, and the datum that often we use is WGS 1984. You will learn more about the datum later on in this video. For example, if I want to locate India in degree minutes seconds, that will be 28 degree 38 minute 41.2800 seconds north and 77 degree 13 minutes 0.1936 seconds east. Now let's understand what are the problems faced while doing projection. So there are two things into this. First, we'll be converting 3D globe into 2D map on a paper or on a computer screen. Secondly, while converting 3D globe to map, there is certain kinds of distortion which occurs. It is similar to that of orange. Suppose if you have an orange and you try to peel it out, so if you are peeling it in vertically, you will have different shape, and if you are trying to peel it into circular fashion, it will be different shape. In the either case, there will be distortion of the shape. Now, the distortion can be in various forms. One is the distortion of the shape if the shape changes. The second is if the area changes. Third is if the scale changes, and the fourth is if the direction changes. It is not possible to preserve all these properties. To solve this problem, we basically have three families of map projection. First, there is cylindrical projection that is designed to preserve distance and areas. If you imagine a globe and fold a sheet of paper around it in a shape of cylinder and project everything that is on the globe to the cylinder that surrounds the globe, and then we cut the cylinder open, then we get cylindrical projection. Second type is the conical projection. In this case, we fold a sheet of paper in the form of cone or hat around the globe, and we project everything that is on the globe to a sheet of paper and cut it open. Then we have conical projection which preserves angles. Third is planar projections. It preserves distances. So if we have a globe, we can put a sheet of paper in one of the side and project everything from the globe to a sheet of paper, and that is the planar projection. All the projections have advantages and disadvantages. and there are distortion of angular conformity, distance and area. So we can minimize the problem on one distortion by choosing certain projections. There are also projections that compromises all distortions, which still means there is inaccuracy, but it minimizes all the distortion of areas, angular conformity and distance. Example is this Robinson projection, which is been displayed in the figure. If we want to preserve angles, we use conformal or orthomorphic projections. The famous one is the Mercator's projection, which we can see here on the figure. It is very oftenly used as a school map in USA and used for navigations or for meteorology. The problem is that it results in distortion of proportion of the area, and the distortion can be larger if we are farther north or south of the equator. For example, let's look at the Greenland. It looks as larger as the whole continent of Africa. A very frequently used projections in this group of projection is Universal Transverse Mercator's projections or UTM. It is a global projection, so we can use it for any location on the globe. It is divided into 60 equal zones, each 6 degrees wide in longitude from east to west, and it starts numbering with number 1 at the international date line and goes up to 60. When we use it, we need to indicate if it's north or south of the equator. The origin is on the equator at a specific longitude that changes using false northing and false easting. So the north and the south are used in the indication of projection to distinguish between northern and southern hemisphere. For example, if we are looking at Uganda, it's in UTM zone 36 north, and then we can express the location of Kampala as 452,611 meters east and 36,127 meters north. In this figure, we can see Netherlands, that is in the UTM zone 31 north. It depends on the location you need to use in different datums. So in US, we use North American datum. In Europe, we use WGS 1984. In Africa, around the equator and East Africa, we use Eckert 1960 datum, and so on. We have many more datum, not only this. There are also projections with equal distance. The equidistance projections keep the scale constant. The distances are accurate, and the examples are the equidistant cylindrical projections, azimuthal equidistance projections, and some others. They are basically used for radio and seismic mapping, navigation, etc. And the example of this projection is this United Nations logo, which is azimuthal equidistance projections. So the distances are preserved, but of course the distortions are large from the centers. So there are also projections with equal areas, where the areas are more proportional. As you can see, the mold-wide equal area cylindrical projection, where Greenland is now more proportional to the continent of Africa. But it gives a lot of distortion in the shape of angular conformity. These maps are often used in the mappings for education or as a general reference. If we use projections, we need reference level. And the problem is that the globe is not a perfect sphere. So we can use spheroid, but it will not be a good fit. We can also use the ocean level, but that is also not very constant and very difficult to use, of course, at land. Then there is a reference ellipsoid, which is a fit. We can use local plumb line, or we can use continents, or we can use geoids. Geoid is the Earth's gravity field, which is also not constant but is very accurate reference. If you want to measure the reference elevation at a very precise level, for most purposes, we use the datum which is localized approximation of the ellipsoid. So, examples are WGS 1984, Eckert 1960, North American datum, and so more. You will learn more in details about spheroid, ellipsoid and geoid in next video. I have already mentioned about false northing and false sisting. What it means is best illustrated in Dutch projection which is called Amersfoort. Originally, the origin of this projection was a church in Amersfoort, city in the center of the Netherlands. However, there was a problem for the people using it offshore, like the Navy, because they had to deal with negative failures. So instead of redefining completely the origin, they moved the origin artificially by introducing false northing and false easting. Since 1970s, the origin has been moved with false northing of 155 kilometers and false easting of 463 kilometers. And since then, all the territories of the Netherlands are in positive values. Now to resolve this projection, which one will we choose? Well, that depends very much on the different factors, that you are studying specific country or it's a region consisting of multiple countries. If it's a specific country and you are doing this project for government, normally we use national projections. And if it's more regional, then it's often more useful to use global projections such as UTM. Different projections have advantages and disadvantages. And definitely if we do analysis work with elevation model or do measurement, it is not a good idea to use the latitude and longitude but to use projections. It also depends on the availability of data. If a lot of national data is available, then we stick to national projection, and if we rely on global data a lot, then it's better to stay in the global projection. That's all. I hope you liked the video. Stay tuned. Hello everyone and welcome to GIS. Today in this video I would like to introduce you to the few terms that are related to the shape of the earth. At first let us understand what does spheroid means. The earth is not perfect sphere, so the earth is not completely spherical with the circumference of 40,075 kilometers. That would actually make a lot of things easier if the earth were perfectly spherical, but it's not. There is of course a topographical variations which includes mountain, valleys, hills, etc. when we are talking about in comparison to the rest of the diameters of the earth. Even the tallest mountain do not really gives the whole lot of variations. So actually if we are going on, we are talking about three-dimensional representations. We actually often have to exaggerate the topographical variation of different areas or you get to slow up. So yes, there is a topographical variation, but when we are talking about the entire earth, it's not very much taller. Our values are not much lower than the surface of the earth. For example, the peak of Mount Everest is only 8,848 meters above the sea level, compared to the Earth's diameter of approximately 12,756,200 meters. So as far as the topography goes, when we are talking about the shape and the size of the entire Earth, we do not have to worry about that too much. What are the things that we have to worry about is a fact that the earth is squashed. The earth is actually little bit shorter from pole to pole direction than it is if you are talking about diameters. As you can see in the first diagram, the earth is squashed. This is enough to make certain things when we are doing geographical information system much more difficult than if we were working with a perfect sphere. Even though our planet is sphere, it is not perfect sphere because the force caused when the earth rotates. The North Pole and the South Pole slightly flat. The Earth's rotation, wobbly motion, and the other forces are making the planet change the shape very slowly, but it still rounds. The squashness of the Earth gives us what's called as semi-major and semi-minor axis. If the Earth were perfectly spherical, then we would just talk about the diameters and the radius, and that would be constant in all directions. But because the Earth is not perfectly spherical, we have semi-major axis that goes from equator to the other side of the equator, and the semi-minor axis which is shorter, which goes from North Pole down to the South Pole. So what we call a shape, there is a sphere that we took and squashed it a little bit. Well, if we talk about sphere and squashed it, it forms ellipsoid. So that's the terminology we use. So say we are trying to construct a model of the earth. Many times when we are talking about the precious measurement, which is not based on sphere, but it is based on little bit squashed sphere called ellipsoid. Sometimes it is also called a spheroid because it is so close to sphere, it's almost a sphere. So sometimes we can hear the term spheroid as well. But both the spheroid and ellipsoid just means you have taken a sphere and squashed it little bit. And we have little bit better representation about the shape of the earth. The spheroid is three-dimensional shape created from two-dimensional ellipse. The ellipse is an oval with a major axis that is the longer axis and the minor axis that is the shorter axis. As you can see here in the diagram, we have the shorter axis that is the minor axis and the longer axis that is the major axis. For example, if we rotate the ellipse, the shape of the rotated figure is the spheroid. There is another term. It is also true that earth is not only squashed but it's also lumpy. These are the technical terms. The earth is squashed and lumpy. Aside from the topography, the earth have little bit bulge, little bit lumps across the surface of the earth. So here you can see the lumpiness of the earth. Sometimes it's very important to count for those lumps across the surface of the earth. When we are doing that, we are generating something called geoid. So, geoid is the count of the lumpiness of the earth as well as the squashness of the earth. Now at last, let us understand different ways of models and the shape of the earth. The sphere is a representation of the earth and one level of generalization. If we want to get little bit better than that, we squash the sphere little bit and we get it into an ellipsoid. And if you want to make it even better representation of the earth, then we go take into counts its lumpiness and squashness, and so we produce a geoid. That's all. I hope you liked the video. Stay tuned. Hello everyone and welcome to GIS. As in the previous video, we have talked about spheroid, ellipsoid and geoid and how are these things estimated the shape and size of the earth when we are working in 3 dimensions. And now let's look at how that represented inside ArcMap. It's unfortunate that in places ArcMap will, as far as conflict, the way the data is stored and the way the data is displayed. So to make that we can separate those out because conceptually they are very separate things. As you can see, the ArcMap is open. Now go to Add Data icon and click on it. The Add Data dialog box is displayed. In this dialog box, browse to the location and then select the country shapefile and choose Add button. The dialog box is closed and the shapefile is added in the data view area. What assumptions were made about the shape and size of the Earth when the GIS data is collected? It is very important to think and to consider because if we don't think about that, we can have major impact on the accuracy of your analysis. Now let's go to table of content and select the shapefile and then right click on it. A flyout is displayed. From the flyout, select property option. The layer properties dialog box with source tab chosen is displayed. So here in the source tab, it does give some basic information about the size and the shape of the Earth when this data was created. And we see this under this term Geographic Coordinate System, that is GCS WGS 1984. GCS is just the ArcMap abbreviation of Geographic Coordinate System, and WGS in this case stands for World Geodetic Survey, and this is the World Geodetic Survey of 1984. Of course, periodically we update and receive our survey for planets and our estimation of its size and shape in order to be able to get better coordinates. And that is why if somebody just says that some particular location point A is at 35° north and 16° east, that's not enough for you to be able to place that point because you do not know what assumptions about the size and the shape of the Earth were being made when that measurement was taken. This is very important with GIS data. Somebody just gives you latitude and longitude, that's not enough. We need that other information about those assumptions, the size and the shape of the Earth. So this is telling us that the points of the latitude and the longitude that are making up this file, they all are connected to make the country file here. They all are collected according to WGS 1984. This is very popular system for GIS data and collecting data from across the world. In fact, the Global Positioning System uses WGS 1984, whatever may be the latitude and longitude. You could go to a lot of detail about understanding what assumptions that WGS 1984 is making. You probably should. But for right now, it's enough to know that this particular GIS data file, all of its points and all of its geometries and all of its lines can be correctly positioned as long as we understand that it is in the context of all of its assumptions of WGS 1984. Now let me close this dialog box. Next, we have another thing that we should know. Go over to the table of content and right-click on the layer icon. A flyout is displayed. From the flyout, choose Properties option. The Data Frame Properties dialog box with Coordinate System tab chosen is displayed. Here we can see two major folders that the ArcGIS has. First is Geographic Coordinate System and the second is Projected Coordinate System. And this is one of the places where ArcGIS gets terminology somewhat confused and we start to get that conflict between the assumptions and the size and the shape of the Earth and how we display the data through this projection. And one of the reasons that we start to get the confusion is because ArcGIS calls both of these as coordinate systems. So as we can see, we have the first folder Geographic Coordinate System and the second is Projected Coordinate System. I want to continue to talk about this folder Geographic Coordinate System. Now expand Geographic Coordinate System So here you can notice all the places around the planet. And then there is world as well. So just expand world and scroll down. And we see WGS 1984 as well as whole bunch more. These are basically of the different surveys, datums, geoids, ellipsoids, all of that ArcGIS understands for displaying data. So it's very good that the ArcGIS understands World Geodetic Survey of 1984 because I said so much. Including the GPS satellite uses WGS 1984 to record its coordinates, but far from only the system that we might have. So we do have other World Geodetic Survey, that is WGS 1972 and WGS 1976 and many more. As you can see here, whole bunch is given. So you might end up with different GIS data that uses different sets of assumptions. And what's very important here is to make sure that this things matches. And actually, GIS does not really help you to integrate all of this data and any kind of automatic way. You have to know what you are doing, because if we end up with different sets that are using in different sets of assumptions about the size and the shape of the earth, it will even try to overlay something about a completely different way and not able to do this conversion. But I also want to show you over here we have whole bunch of different coordinate locations like Caribbean, Asia, Africa, South America, and many more. Now expand Europe folder. We can see here Estonia, and then here we have Hungarian datum 1972. We have all this different system here for specifying locations on the planet. So WGS, World Geodetic Survey, is a system for specifying latitude and longitude according to entire planet. They try to come up with the size and the shape of our Earth that is pretty good across the entire planet for giving the latitude and longitude coordinates. But that is the case that in different situations, if we are not worried about mapping across the entire planet, maybe you were worried about what we saw in Estonia or maybe any individual places. You may not care about trying the approximity of the entire earth well enough to give the coordinates over, and so I want to come up with the models of the size and the shape of the entire earth. But a part of the earth that I am mapping, and say I am mapping for a particular country. And so we may do this to make a sophisticated model for giving accurate latitude and longitude as long as we are within the certain area. So like we were looking at Estonian system here, maybe if we are working with GIS data or we are mapping in Estonia, we might want to use those if it is very accurate for that area, using a set of assumptions that closely approximate the surface of the earth in Estonia. So what we may do if we are working with some particular region, it may be fantastic idea not to use some kind of worldwide system, but to use the system that was designed for mapping your area, because that's going to provide us much more accurate coordinates within that area as long as we are outside and use it for something that you are not intended for. But also ArcGIS understands all these different systems. So if we end up downloading data of some places and we need the data of some other place, it could be one of this regional system which ArcGIS will understand it, but it will not automatically convert it. It will understand it, but we need to do the conversion. For example, if you got some data of Luxembourg 1930 and you are trying to integrate within some European worldwide data that is using general European datum, so for that you need to convert those one system or convert one system to the other system. in order to make sure that it aligns most accurately. Because ArcGIS does not just do that for you. They understands this, but that does not mean that you just throw a bunch of data which uses whole bunch of different systems into your project and get them to correctly align, because they do not have to start to get positional errors. And basically what I want you to understand is this geographic coordinate system folder is all about assumptions of the size and the shape of the planet when we are collecting data. And this folder, projection coordinate system folder, is really what we call projection in geography. This is what we are going to display in that data. And this is very important coordinate system. This is about how we are going to hold that data, and this is about how we are going to display that data in map format, that is in two-dimensional format. So when we are talking about GIS data layers, they should have coordinate information that comes out of this geographic coordinate system folder, because that's how we are going to know what sort of assumption was used when the data was collected, so that we would able to pair that with a particular projection when we want to display it in map format. I hope you liked the video. Stay tuned. Hello everyone and welcome to GIS. Today in this video you will learn about projections and how to correctly use the projections in ArcMap. Projections are of course how we display the information about the Earth. The geographic data that we have about the Earth is three-dimensional. Of course, the Earth is spherical, so often we display two dimensions on a map or even on a computer screen. As you can see here, the ArcMap is open. Now let's add the data. For adding the data, go to Add Data icon in the standard toolbar and click on it. The Add Data dialog box is displayed. In this dialog box, browse to the location and select the shapefile of the countries of the world and then choose on Add button. The dialog box is closed and the shapefile is added in the data view area. As you can see here, it has been added. So here you can see the representation of three-dimensional Earth on two-dimensional computer monitors. That must mean that we are going through some kind of transformation in order to display in this way. So now let's look at how ArcMap handles these projections. Go over to Table of Content and right click on the layer icon. The flyout is displayed. From the flyout, choose Properties option. The Data Frame Properties dialog box with Coordinate System tab chosen is displayed. And here in this box, click on this minus in order to see the two major folders, Geographic Coordinate System and Projected Coordinate System. And this folder, Projected Coordinate System, is basically what I would just call projections. The major distinctions that used to be made here, although the ArcMap will confuse this if we let it in, that our data should be stored in what is called as Geographic Coordinate System. When we looked at this in the last video with the countries of the world, we saw all the data were stored according to World Geodetic Survey of 1984. But how we choose to display that data should be according to the transformation that we find here in the Projected Coordinate System folder. Now expand Projected Coordinate System folder. So look into the folders. We will start to see things that will probably look a lot more familiar. especially if we look at the world folder. So expand world. It seems like that the kind of things that we recognized as projections. As we can see here, Eckert, equidistant conic, equidistant cylindrical, Marcator, Miller cylindrical, Robinson, and many more. We have whole bunches given here. This thing starts to look like the kind of things that we think up as projections, and that is why they are. So we can choose any one of this, and for the purpose for the display of this projection, the ArcMap will transform the data according to the equations, that is the projection, in order to display it in the computer screen, as you can see here now. Now before I click and show you that, I want to show you one of the peculiarities about the programs. Notice down here we have the current coordinate system, and that reports what is the current coordinate system of the data frame. And this is where the ArcMap will really start to get the difference between how we are going to store three-dimensional data, or first is how to display the data in two dimensions. Confused? Now close this dialog box. So you can notice that it has to be the case that since looking at this world data here on two dimensions on the computer screen, it has to be projected. There is no any other way around. And of course, this is the computer system. You probably think they have done something systematic to transform that data on this two-dimensional surface, which of course it has. So you might be tempted to ask them what projection did it use in order to display this data. It must have done something. Well, ArcMap is unfortunately rather opaque in that kind of thing. Because if we go over to layers, difference between a particular data file, we know how the data has been stored. So let me show you that. Now go over to the table of content and right click on the layer icon. A flyout is displayed. From the flyout, choose Properties option. The Properties dialog box with Coordinate System tab chosen is displayed. The properties under this layer should tell the information about how it's being displayed, but it really doesn't. When the Data Frame Properties dialog box opens, it tells it's using WGS 1984, but WGS 1984 is not a projection. It's not the way for displaying that data in two dimensions. So what the ArcMap is doing, it's just taking all the points in the data file as a plotting of latitude and longitude, as if the latitude and longitude were cadastral grid coordinates. Now let me close this data frame dialog box. A cadastral coordinate system is a coordinate system that specifies each point uniformly in a plane by a set of numeric coordinates. And the numeric coordinates may be the latitude and the longitude, that is x and y value. So yes, this is technically a projection, and in fact one of the easiest way that you can make the projection in just to assure that the spherical latitude and longitude coordinates are the cadastral grid coordinate, and just plot them in two-dimensional space. When we do that, the projection that results does have some peculiar properties, and we go and look that in more details. But rather, when we were trying to display the data, we were trying to change the projections that make sense. Go over to the table of content and right click on the layer icon. The flyout is displayed. From the flyout, choose Properties option. The Data Frame Properties dialog box with Coordinate System tab chosen is displayed. In this dialog box, go over to Projected Coordinate System and expand the folder. Because this is world data, so scroll down and expand world folder. And here you have so many projections, as you can see. So let's display it according to Robinson, which is compromised projections. Now choose Robinson projection and then click on Apply button and OK button. The dialog box is closed, and here we go. It has done a mathematical calculation on the data in order to display it according to the equation that are the Robinson projection. Very importantly, if we go over to table of content and right click on the shapefiles of the countries of the world, a flyout is displayed. From the flyout, choose properties option. The layer properties dialog box with source tab chosen is displayed. And here you can see nothing has been changed about the data. The data is still latitude and longitude points that have been collected according to the specification of WGS 1984. So, close this dialog box. Again go over to table of content and right click on the layer icon. A flyout is displayed. From the flyout, choose properties option. The data frame properties dialog box with coordinate system tab chosen is displayed. They are now just being shown here on the computer screen according to the method of Robinson projection. That's the distinction between how we store data and how we display data. Now, if you want to change the projection again, choose Marketers Projection and then choose Apply button and at last choose OK button. The dialog box is closed, so now here we are using Marketers Projection. This is project specific, so we can save out this project and keep all the data according to one projection for the purpose of the project and then use the same data in different projection in different project. That's all. I hope you liked the video. Stay tuned.